Hello, welcome to this quick tour of transition metals for A-level. The clip is not designed to last very long, just have a quick run through of all the different things you need to be aware of. So this flowchart attempts to put it all into one space, one place you can look at, and I'll just quickly run through the various parts of the flowchart to remind you of what you need to be able to revise and remember for each one. So in terms of definitions, as a bare minimum, you should know off by heart what the definitions and meanings are of those five words or phrases: transition element, coordination number, coordinate bond, complex, and ligand. So in order to qualify as a transition element, they have to have an electronic configuration that shows they have at least one stable ion with a partially filled d subshell. So looking at scandium, for example, it's got one stable ion at 3+, and if you look carefully you'd have to take away an electron from the 3d subshell in order to achieve this, so it can't be seen as having one stable ion with a partially filled d subshell, so it's not a transition element. If we also have a look at zinc, so remembering that s electrons get removed first, if we go from Zn to Zn2+, the d subshell remains intact, so it's not an ion with a partially filled d subshell. So if you look quickly at a energy level diagram, you can see that 3d and 4s actually overlap, so there's quite similar energies between them. But it's important to remember that 4s always empties and fills first because s electrons have the lowest energy in any energy level. So let's now move on to the characteristics of transition metals. We've got three. We've got catalytic behaviour, we've got variable oxidation states, and we've got the formation of coloured complexes. So let's start with catalytic behaviour. This is based on the fact that in the d subshell you get partially filled or empty d orbitals, and what this allows the metal to do is to hold electrons temporarily to form intermediate species within your pathway of a lower activation energy. That's key to the way a catalyst works. So you've got three processes that might be worth remembering. You've got the contact process, the Haber process, and the hydrogenation of alkenes. So what we've got there is what each process actually involves, and the actual catalyst. So you've got vanadium pentoxide or vanadium 5-oxide for the contact process. You've got finely powdered iron for the Haber process, and finely divided nickel for the hydrogenation of alkenes. So it's definitely worth maybe putting them on a flashcard and remembering them, because all three come up in the OCR specification. So with variable oxidation states, it's a similar story. Different numbers of electrons can be made available for bonding. So if we take a look very briefly at the various number of oxidation states each element can have, it's no coincidence that ions containing chromium and manganese are amongst the most powerful oxidizing agents. I'm of course referring to the commonly known examples of dichromate 6 and manganate 7. Let's now quickly look at coloured complexes. Now this is where we go back to some of our definitions. So let's look at an example of a complex. Most transition metal complexes start with the idea of a central metal ion made of a transition metal, and it's surrounded by up to 6 ligands. So all ligands have a lone pair available for a dative covalent bond. So a dative covalent bond between a ligand and a central metal ion is called a coordinate bond. So you don't have to draw the arrows indicating the dative covalent nature of the bond in the exams, but you should definitely draw the square brackets and the charge in. The square brackets indicate that the complex ion contains a number of different species, and the charge indicates that it's actually 2+ charged in this case. So the charge can be worked out by a combination of the charge on the ion, the transition metal ion, and the charges on the ligands. So be mindful that although water ligands are not charged, some others are. So this example is probably a little more complex than you'd expect at A level, but you could call it potassium iron 3 ethane dioate. So the ethane dioate ion is 2- charge, so 3 of them against 1,3 plus potassium, 1,3 plus iron, beg your pardon, would lead to a 3- charge on the ion overall. So the iron 3 ethane dioate ion has a 3- charge, so it needs 3 potassiums, 3 potassium ions that is, to balance that charge out. So on the oxygens that you can find on the ethane dioate ion, that would lead to 6 coordinate bonds. So that would give us a coordination number of 6 for this particular complex. So when you get more than 2 pairs of electrons in one complex ion, more than 2 lone pairs that is, that ion is called multidentate. Classic example is EDTA. So EDTA stands for ethylene, coming from the 2 carbons in the centre, the D coming from diamine in respect of the 2 amine groups at either end of the CH2-CH2 chain, is the old name for ethanoic acid, so you can clearly see that there's 4 ethanoic acid molecules coming off the corners there. Okay, so let's now move on to the different colours that you need to be aware of. So in the first instance, colour arises in transition metal complexes because the D subshells in the transition metal split and rearrange themselves to accommodate coordinate bonding. What happens as a result is the energies of the electrons change, and then certain light frequencies within the visible spectrum are absorbed or reflected. But it's worth pointing out that this isn't actually needed for A level, it's just a sort of interesting explanation of why the colours are seen. So let's now look at the actual colours we need to remember. So these are some of the common colours of the solutions of the ions. So these are all ions where they have a central metal ion and 6 ligands around it. So the colours now remaining are the ones you need to remember for OCR. So let's just summarise them. So you've got Fe2 plus pale green, Fe3 plus orange, chromium 3 plus violet, Cu2 plus blue, and Mn2 plus light pink. These are the colours of the hexaaqua ions in solution. And these are the slight alterations for the formation of the hydroxide precipitates. So the reactions can be split into ligand substitutions or precipitations. So there's a subtle difference between the two. A ligand substitution occurs when everything stays in aqueous solution, but one ligand substitutes for another. Or should I say, really one or more ligands substitutes for another, but all species remain in aqueous solution. With precipitation, the substitution results in a solid product that's insoluble in water. So in order for ligand substitution to happen, the transition metal species remain charged and therefore attracted to polar water molecules, and as such remain dissolved. So the ligand substitution in precipitation reactions leads to a neutral species to which polar water molecules are not as strongly attracted, hence the precipitate. So a typical example might be Fe2 plus reacting with sodium hydroxide to produce iron 2 hydroxide precipitate. So in this species you've got one iron 2 plus ion, 2 hydroxide ions, therefore the charges balance each other out. Overall there's no charge, so therefore you get a precipitate. So moving on to stereoisomerism, let's just remind ourselves what it means. So what I want to do now is go through the stereoisomerism that each type of shape of complex actually forms. So you've got octahedral shape, tetrahedral shape, and square planar shape. So So just to clarify, octahedral, tetrahedral and square planar are shapes, not forms of stereoisomerism. Okay, so let's go through each one in turn. So this complex has all the same ligands all the way around, so it has 6 water ligands and 1 cobalt central metal ion. So there's no stereoisomerism going on. So this has a coordinate number of 6 because there's 6 coordinate bonds, bond angles of 90 degrees all the way around, and its shape is octahedral. These pair of isomers still have the same information applying to them, but if we look quite carefully you can see that there's different ligands around the central metal ion. So the orientation of the identical ligands determines whether it's cis or whether it's the trans isomer. So what we're looking at here is 2 ligands are the same and the other 4 are different to those 2 ligands. So the 4 other ligands need to be the same as each other. For example, in this one you've got 4 times NH3. So if you've got 3 of the same bidentate ligand in an octahedral complex, they can exhibit optical isomerism. But in order to score full marks in your exam question, you've got to make sure that your 3D mirror arrangement is clearly drawn, with your dotted lines, your wedges, and also the connectivity between the correct atoms on the ligand. So for example here the coordinate bonds must be clearly between nickel and nitrogen because it's the nitrogen atoms that possess the lone pairs. So let's now move on to tetrahedral and square planar, and that'll be us done. So in this shape, just like normal tetrahedral molecules, the bond angle is 109.5 degrees. The chloride ligands are too large to fit 6 of them around the central Cu2+. So the maximum that you can fit there is 4. The reason for this is the chloride ion is actually much bigger than the chlorine atom because the extra electron causes repulsion between the adjacent shells, so the whole thing swells in size. So finally we've got the square planar complex arrangement. So 90 degrees in one plane, but 180 in the other. So like before, cis is the same ligands 90 degrees apart, trans is the same ligands 180 degrees apart. So this would be a cis isomer. And an important example of a square planar complex to remember for OCR is cisplatin. It does pop up sometimes in questions. So what you'll need to be able to say is that it works by interfering with the cell division in cancer cells, so therefore killing them. So basically you've got a platinum central metal ion. Platinum is 2+, and you've got 2 chlorides, each one 1-, so therefore it's neutral overall. And the arrangement is that the chlorides are at 90 degrees to each other, and the NH3s, the ammonia ligands, are at 90 degrees to each other. So this takes us to the end of our quick tour of transition metals. I've squeezed, I think, pretty much everything that you need to remember in. Hopefully it's been giving you an idea of what's coming up if you haven't come across this topic before, or if you're using it for revision, maybe the few things you might need to go and look back over. So for now, thanks for listening. Until next time, see you soon.